Tonight, you will close your eyes, lose consciousness for 7 or 8 hours, and remember almost none of it. But a piece of your brain the size of your thumb will not stop working. Not while you dream, not under general anesthesia, not in the minutes after a cardiac arrest when a doctor would describe you as unresponsive. It has been running continuously since before you were born, and it is scheduled to run until the day you die. If it stops for more than a few minutes, nobody will ever wake you again. The structure is your brainstem, at the very base of the brain, where it meets the spinal cord, and the network threaded through it is called the reticular activating system. Its job is the least glamorous and most fundamental one in your skull. It decides moment to moment whether you are conscious at all. Every signal arriving from your body, every sound, every touch, every change in temperature, passes through it, and it decides which ones deserve to reach the parts of your brain that actually experience things. It is not where your thoughts live. It is the doorman, and nothing gets upstairs without it. Nobody knew this until 1949. Two physiologists, Giuseppe Maruzzi and Horace Magoon, were working with cats at Northwestern University, and they ran the experiment in both directions. Stimulate one specific region of the brainstem with a mild current, and a sleeping cat woke instantly, eyes open, brain activity snapping into a fully alert pattern. Damage that same region, and the animal could not be woken by anything at all. Then came the result that overturned the textbooks. The dominant theory held that sleep was passive. The brain ran out of incoming stimulation and idled down like an engine when you lift your foot off the gas. So they cut the sensory nerves feeding into a cat's brain, removing outside stimulation entirely. The animal did not fall asleep. Wakefulness, it turned out, is not something the world does to you. It is something a cluster of cells in your brainstem does for you, every second, against constant pressure to stop. There had been a clue 3 decades earlier, delivered by an epidemic. Between 1916 and 1927, a disease called encephalitis lethargica swept the world and affected perhaps 1 million people. Some slept for weeks and could not be roused. Others could not sleep at all. A Viennese neurologist named Konstantin von Economo autopsied them and noticed that the lesions sorted themselves by symptom. Damage toward the back of the hypothalamus and the upper brainstem produced endless sleep. Damage further forward produced insomnia. He concluded there had to be a sleep-regulating center down there, and he was right, 30 years early. Some survivors spent the rest of their lives frozen in a statue-like state, and became the patients Oliver Sacks described in Awakenings after treating them with L-Dopa in 1969. In humans, the damage Maruzzi and Magoon inflicted deliberately usually arrives by stroke, hemorrhage, or a blow to the head. Cut the ascending pathways out of the brainstem, and the result is coma, sometimes a persistent vegetative state lasting years. The heart beats. The lungs breathe. The cortex is often structurally intact and perfectly capable of activity. But nothing is coming up the stairs, and consciousness has nothing to assemble itself from. The Glasgow Coma Scale, the score paramedics call in from the roadside, is in practice a bedside test of this one system. Can the patient open their eyes, speak, and move on command? Now move the damage a few millimeters, and you get the opposite catastrophe. In 1995, a French magazine editor named Jean-Dominique Bauby had a stroke in the pons, the part of the brainstem that carries motor commands down toward the body. It spared the arousal network. He woke up completely conscious, fully aware, able to hear every word spoken in the room, and paralyzed except for his left eyelid. Over roughly 200,000 blinks, with an assistant reciting the alphabet, he dictated an entire book. That is the difference the doorman makes. Destroy the wiring beside it, and a person is trapped inside a working mind. Destroy the doorman itself, and there is nobody left inside to be trapped. The system is not one thing, which is part of why it is so hard to knock out cleanly. It is a scattered set of nuclei, each broadcasting a different chemical upward. The pedunculopontine nucleus sends acetylcholine. The locus coeruleus, a pair of spots so small and so darkly pigmented that early anatomists named them the blue place, floods the brain with norepinephrine. The raphe nuclei distribute serotonin. Higher up, the tuberomammillary nucleus of the hypothalamus supplies histamine, which is the entire reason an antihistamine allergy pill makes you drowsy. You are blocking a wakefulness signal you did not know you had. All of it converges on the thalamus, the relay that hands the wake-up call to the cortex. In a coma, that chain is broken somewhere along its length, and the alarm never reaches the room. When you fall asleep, none of this shuts down. It changes mode. The gate closes to most incoming traffic, which is why an entire thunderstorm can happen without you, while one narrow channel stays open, monitoring for anything that might matter. This is why somebody can whisper your name across a dark room and you will be awake before you understand why. Your brainstem was listening the whole time. It heard the thunder, checked it against some internal register of things worth waking for, and filed it under no. Then it heard 4 syllables at a fraction of the volume and pulled the alarm. That decision took milliseconds, and you had no part in it. Here is the part that rarely gets mentioned. That register is not a fixed list. It is built out of your own life. New parents sleep through garbage trucks and sirens and snap awake at a faint whimper from a crib down the hall. Not a loud sound, and not a sound that would have woken them 2 years earlier. Night shift workers, soldiers home from deployment, and people living alone after a break-in all report their own peculiar filters. The hardware is identical in every one of them. The threshold is not. Your brainstem has spent your entire life quietly assembling a model of what you personally cannot afford to miss, and it enforces that model every night, while the rest of you is unconscious and in no position to argue. Manufacturers exploit this. Smoke alarms are tuned to the profile the arousal system treats as non-negotiable. Sudden, high-pitched, irregular, repeating. Millions of years of selection built a system that treats a scream, a snapping branch, and an infant's cry as reasons to override sleep immediately without consulting the sleeping mind, and a piece of plastic on your ceiling is deliberately impersonating all 3. Sleep itself is not one state, and this same system is what divides it. In the 1950s, the French neurophysiologist Michel Jouvet found a phase in which brainstem activity looks almost identical to waking. Fast, busy, alert, while the body lies completely limp. He called it paradoxical sleep. We call it REM. The limpness is deliberate. A small brainstem region actively switches off muscle tone so you do not physically act out whatever your cortex is running. Jouvet showed that lesioning that region produced cats that stalked and pounced at nothing while sound asleep. The same failure happens in people. It is called REM sleep behavior disorder, and it comes with a sobering statistic attached. Most people who develop it go on to develop Parkinson's disease or a related condition, often more than a decade later. A fault in the brainstem's night shift can announce a neurodegenerative disease years before anything else does. Narcolepsy is the switch failing in the other direction. It affects roughly 1 person in 2000, and the cause was pinned down through an unlikely research colony. For years, a Stanford lab kept narcoleptic Doberman pinschers that collapsed mid-play, and in 1999, Emmanuel Mignot's group traced their condition to a broken receptor for a then newly discovered neurotransmitter called orexin. In humans, narcolepsy involves losing the orexin neurons themselves, a population of only about 70,000 cells in the hypothalamus, most likely destroyed by the person's own immune system. Orexin is the chemical that holds the waking state steady. Without it, the switch flutters, dropping people into REM sleep within seconds, mid-sentence. In cataplexy, the most dramatic form, laughter alone can trigger it. The person stays fully conscious while the muscle paralysis of REM sleep arrives at completely the wrong moment and puts them on the floor. That discovery has since been run backward. If orexin is what keeps the wake signal switched on, then blocking orexin should produce sleep without sedating the rest of the brain. And since 2014, there has been a class of prescription sleeping pills, the orexin receptor antagonists, that does exactly that. They do not press down on the brain. They reach into the arousal system and switch off the message telling you to stay up. General anesthesia works the same territory with far less finesse. Most anesthetics do not switch the brain off. A brain under anesthesia is metabolically busy, and the cortex remains capable of responding to a direct stimulus. What the drugs do is amplify the inhibitory traffic inside the arousal system until the gate stops passing anything upward. Your cortex is intact, functional, and receiving nothing to be conscious about. This is the most demanding part of the anesthesiologist's job, because the dose has to suppress the relay, not merely the body. When it falls slightly short, the result is anesthesia awareness. The drugs paralyze the muscles and blunt memory formation, but leave a sliver of the gate open, and a patient can be present for part of their own surgery with no way to signal it. When researchers rely on patients reporting it spontaneously, the rate looks like 1 in many thousands. When they interview every patient afterward with structured questions, the figure comes out closer to 1 or 2 per thousand general anesthetics. It is why operating rooms now use EEG-based depth monitors that read the electrical signature of cortical arousal in real time. A routine piece of surgical equipment descended directly from electrodes placed in a cat's brainstem outside Chicago in 1949. Caffeine pulls the same lever from the opposite end. All day, a molecule called adenosine accumulates in your brain as a byproduct of its own activity, and it dampens the arousal system, which is much of why the pressure to sleep builds the longer you have been awake. Caffeine fits the adenosine receptor without activating it, so the sleep signal is still being sent and simply cannot be heard. Nothing is added. A break is unplugged. Amphetamines, prescribed for narcolepsy and ADHD, go further in, boosting norepinephrine and dopamine in the very circuits Maruzi and Magoon first mapped with wire and current. So tonight, when the lights go out and you go with them, the last thing left awake will be a knot of cells at the top of your spine, running a watch it started before you had a name, sorting every sound into worth waking for and not, with no supervision, no gratitude, and no plan to ever stop.